Hello again, everybody. We are talking about exponential growth and decay functions during this video lesson. As you can see in front of you on screen, we're looking at some examples of exponential growth and decay and some notes we're going to be talking about. There are two sides to this. You have exponential growth and you have exponential decay, exactly like the graphs that we just talked about in our first video. On one side, you have exponential growth. So you always have a C value at the front. That's always going to be the amount you're starting with, whether it be 10 and you're doubling it, or you have 20 and you're increasing it by 80%. Whatever that first amount is, it's always going to be this C value. You will also always have whatever is this parentheses part, which will be represented by a B most of the time in general, raised to that little t or x. You will know that it's going to be bigger than 1 if it's going to be growth. The other side of that will be decay. And you will always have the same C as a starting amount. And the parentheses will always be that B value right here that is going to be your growth factor or decay factor in this case. And if you have decay, you will always have it between 0 and 1. Both of these are different versions of the A times B to the X equation, which is the general version of this exponential growth or decay word problems. And that's kind of what you see in this first bullet point right down here, where you have y equals a times b to the x. And that will be something you might see a little bit closer when there's no percents involved. If, for instance, something is doubling, this b value will be a 2. If something is halving, or if it's 1/4 or anything like that, it will just be that fraction that would go along with it. And those are the general notes that you need to know for exponential growth or decay word problems. In the coming problems you will be seeing me go through with you guys, you will see me look at, well, what is the original amount? What is my growth or decay factor? And how many years or what length of time am I going to be using in each problem? And we'll go through some examples together next. In problem 1, you can see that it says a community service club was started at Topsail High School. There were only 8 members total. Every year, the club has been tripling in size. Rate a function to determine the number of students in the club after 4 years. So in this example, we want to underline first what's important. So I will underline the word tripling. That will be certainly important. We also see that there are going to be 8 members in the club to start with, and our time is 4 years. So if we know that our general equation is a times b to the x, no percents here, we want to figure out what the a value and the b value are first. So in this case, our a value is going to be our starting amount, which is our 8 members. 8 members. Our growth factor in this case, we are increasing in size, is going to be tripling, which means it's going to be a 3 for tripling. And our x is years, which we're going to be substituting 4 in for years. And we have everything we need. We just kind of fill in our equation. Y equals 8 times 3 to the x. And to get our answer, 8 times 3 to the 4th, if we grab our calculator, 8 times 3 to the 4th equals 648 people, or members in the case of this problem, which is quite a lot for a community service club. Moving on to our second problem, here, subscriptions to an online arts and crafts club have been increasing by 20% every year. The club began with 40 members. Write an equation to represent the number of subscribers after X years. How many will there be after 3 years or 5 years? So just like last time, we want to underline important things. So we know we are increasing by 20%. So we're going to be using our percent increase formula from our notes we looked at earlier. We are beginning with 40 members, so we'll underline began with 40. And then we're going to need to look at 3 years and 5 years later, so we'll be able to kind of start from there. So we want to write out our percent increase formula first. So we're going to write out C, 1 plus R to the X. And I use X instead of T because it's a little bit easier to follow. The T is a little confusing because of the plus sign. So if we are looking at this problem, we know that C is our starting value. In this case, it is 40 members. Our R is our percent increase as a decimal. So we're going to write 20% would become 0.20 for 20%. And we have made our equation. Our equation we're going to write our equation out. Y equals 40 times 1 plus 0.20 and raise that to the power of X. We've made our equation, which I'm sure you would know this, but we can also write that as 40 times 1.20 as well. Those are equal. And now to find our two answers. Our two answers that we'll end up finding would be 1 where X is 3, which if we place that in our calculator, we would know there are 69 subscribers. And for the second part for 5 years, we would be able to find 40 times 1.20 to the 5th power. And that is going to give us 100 subscribers. 100. Now we're looking at number 3. So let's kind of move up our page a little bit here. Cost of shoes at Nike has been increasing based on inflation by 5.1%. How much would a pair of $50 pair of running shoes cost in 25 years from now? We got to underline what's important. So now we are another increasing problem, increasing by 5.1%. We have an initial value of $50, and our years are going to be 25 years from now. So the tricky thing here is that percent has a decimal involved, so we'll start there. If our decimal percentage is 5.1%, we got to move that decimal place over to the left twice. So we would have 0.051 as our R value. Our C value is going to be the $50 we're spending on the shoes. And let's put those in that same equation from number 2. So we would have 50 times 1 plus 0.051 to the X. And we'll just leave that equation alone and put that 25 in for X. And we are going to be finding an answer of $173.40, which sounds about right for the cost of Nikes around this time in our world. We have reached our 4th problem here as an example. So in this case, we have Sam opening a savings account that is compounding at a 3% rate In a later chapter, we'll talk about how compound interest might be a little bit different and a little bit more advanced and see how it might be more accurate to the real world. But we'll keep it simple for now. So if we run an equation here, we have our 3% increase, and we have P for principal amount and T for time. So pretty easy, we can write our equation here as y equals P times 1 plus R equals to the T, or we could use the percent they gave us as 1 plus 0.03 to the T, using what we already know. So now in part B, we have Sam opening an account with $500 and made no deposits and no withdrawals. How much is the account after 10 years? Well, we can put that 500 into P. We can put the 0.03 in again, and 10 years for that top part there. And we would find that you would have $671.96. So quite a bit of increase in 10 years, $170 more. What is the least number of years it would take for Sam to double his $500 investment? So there are a few ways to do this, and we're going to do it all on paper here, as you would expect from me in class, I would say. So if we are starting with $500, doubled would become obviously $1,000. So we're trying to see when it's going to equal 1,000. So we would have 500 times 1.03 from above to the x. And we got to figure out what x value is going to make that happen. And for this, you're really just going to do some guess and check. We're going to learn how to solve this more specifically later on. We need to use logarithms, which we'll learn about later this chapter, to actually solve for a precise amount. But it turns out that if you keep trying some x values, you would find that between 23 and 24 years would be enough. We have our last two examples of the video here on exponential growth and decay word problems. So now those of you guys who like biology, we have a biology example here where we have the initial number of bacteria in a culture is 12,000 of them, and they are doubling. So we've talked about that before. Our growth factor is going to be a 2 for when it is doubling. So this is our B value. Our initial amount is 12,000, our A value, and we've already got our answer for the equation. 12,000 times 2 to the x, meaning that we can just do 12,000 times 2 to the 6 for 6 days. And we are going to put that right into our calculator and find that the answer after 6 days would be 76,800 bacteria, increasing very, very rapidly. So now in this next problem, we will kind of look at a growth rate of 5% per year on a graduating class of 4,000 students at a local college, we'll say UNCW, in 2008. So we want to look at how we write out an equation for years after 2008. So we want to make sure we're underlining that last part as the definition of our variable t, years after 2008. And we're going to write 4,000 as our initial amount. We have 1 plus our percent as a decimal, and T being years since 2008. So we've seen today lots of different word problem examples of how to find exponential models for a real world scenario. We figured out how many things will be around, or what the value would be after a certain amount of time or years have taken place, depending on if it's growth or decay. And you guys hopefully will have learned something from this video on exponential function word problems.